All right, guys, here's a quick rundown of the notes we took over exponential functions over several days, but this is all in one video, so it's quick and easy to see. So as we worked through exponentials, we kind of discovered this basic format that they follow. You have a number times another number raised to the x power. This is why they're called exponentials, because the x is an exponent. And what we discovered as doing examples and discussing things is that that front number always ties to your initial value, your y-intercept in the situation. What did you start with? Exponential functions are constantly being multiplied by a constant value throughout. So maybe you have rabbits that are constantly tripling in population, or something that's always doubling in size. That is what is happening along the ways, because every value you're multiplying and multiplying. We discovered that if that back number that's being raised is greater than 1, you're talking about a situation that is growing. If that number is less than 1, if you're multiplying by a half every time or multiplying by 1/4 every time, it's actually decaying. It's getting smaller and smaller. And then you do have this weird situation when you're talking about infections and R naught situations, where the direct R naught is not in the formula. You have to add one to it, and I'll explain that when I go over some examples. So first, just to kind of look at some real world examples of kind of how this works is, all right, let's say we have a forest that starts with 10 trees. And the population is tripling every year. Whatever type of tree that is, that's what we have going here. So at 0 years, you would have 10 trees. That is what we are initially starting with. After 1 year, it says that my population is tripling. So if I take those 10 trees and I triple it, I end up with 30 trees. That came from doing 10 times 3, okay? Then to get the next one down the line, it would triple again. So after year 2, we would have 90 trees. I tripled it. So I took what I had, that 10 times 3, and I multiplied that times 3 again. Okay? So I've multiplied by a couple different 3s. In year number 3, I would triple that population again to get 270. So I take what I had, 10 times 3, and I multiply by 3 again, and now I've tripled it 3 times. So in year number 3, I have tripled 3 times, and then you just continue on that path. So if I triple 270, I end up with 510. That is not right, is it? It should be 710. No, 810. Oh my gosh, I'm sorry. So we get to 810, and again, because I started with 10, I tripled it for year 1, I tripled it for year 2, I tripled it for year 3, and now I've tripled it for year 4. And so if I go to write a generalized formula for this, I say, okay, well, to get my y value, to get the number of trees, I'm going to start with 10, and then I'm going to multiply by 3. And the number of 3s I'm going to multiply by is however many years I have let it gone through, because this is just 3 times 3 times 3 times 3. I could call 3 to the 4th. Okay, so it's like 10 times 3 to the 4th, because I'm on the 4th year. On the 5th year, I would do 3 to the 5th, because I've multiplied it by 3 5 times. Okay, so that is what the formula would look like. You started with 10, and every time I have a growth rate of tripling. Okay, that's what multiplying by 3 means. All right, so let's see what happens in a decay situation. We have a 64-team tournament, and we eliminate half the teams every round. Well, so at round 0, before I've played any rounds at all, I start out with 64 teams. After 1 round, half the teams have lost. So I'm going to divide that by 2 to get a total of 32 teams. After 2 rounds, I divide by 2 again. Half the teams have lost, and it drops to 16. After 3, I end up with 8. After 4, I end up with 4. After 5, we drop to 2, and then it would only take 6 rounds. Again, I'm just dividing by 2 every time. So one way we wrote this in class is everybody said, well, I'm going to start with 64. And then if I'm dividing by 2 over and over and over again, I'm dividing by 2 raised to the x, rather than saying divide by 2, divide by 2, divide by 2. But we also said dividing by 2 is the same as multiplying by 1/2. So really the better version of this formula is to say I start at 64 and I'm really multiplying by a whole bunch of different halves, okay? Multiply by a half, cuts it in half. Multiply by a half again, multiply by a half again. Okay, so this is an example of actually a decay rate. Decay just because it's getting smaller as I go on, okay? Let's look at an infection situation. Smallpox has an R0 of 3. R0 is just how many people everybody infects, okay? So I start at 0 cycles. There are 2 sick people. And this one I'm going to kind of draw because it's kind of hard to wrap your head around. So there's my 2 sick people. And R0 of 3 means he gets 3 more people sick and he gets 3 more people sick. So if I actually count after 1 cycle, you might be tempted to say, oh, so there's 6 people sick. But you've got 6 new people sick plus the original that I had 6. So that's actually a total of 8. Now here's where my picture gets weird. So now I have 6 new people sick for a total of 8 people sick. He's going to get 3 people sick. He's going to get 3 people sick. He's going to get 3 people, 3 people, 3, 3, 3, 3. And so now in round 2, I actually have 3, 6, 9, 12, 15, 18, 21, 24, 25, 26, 27, 28, 29, 30, 31, 32 sick people. All right? So now if I start looking at a pattern, well, the shortcut is that I multiplied by 4, and I multiplied this times 4. So in round 3, if I multiply by 4 again, I get 128 sick people. So my formula would be, okay, I start with 2 people, and I'm multiplying by 4. Oops, I tore my paper. Over and over and over again. So 4 raised to the x. So here's the catch. With R0, the shortcut is you always have to add 1 for the growth rate. All right? You can't just use the R0 as it is. You add 1 for the 1 original person you had sick. All right? Okay, so that's kind of how to write them from word problems. I'm going to come back in another video and talk a little bit more about the graphs of exponential functions, and hopefully that will kind of help clarify that, okay?